Okay, good morning. This is the first of a series of lectures on convection heat transfer. I have planned to make some notes, and I have already given out some set. I'll be making some more notes and problems and solving some of them in the lectures here also. We will cover a very vast array of issues and problems, starting with forced convection, free convection, then going on to boiling, condensation. So it's a very large canvas to cover. So what I will be doing is concentrating on the big picture and giving out how we approach convection problems and how we solve them and why do we do it that way. So today I will begin with an introduction and give you some examples of applications and what type of issues we have to ask. Then we'll look at what is the approach by which we solve these problems. And then I'll talk about the importance of boundary layers. So we'll begin by looking at some applications, and I've taken these from many different things. So let's start with something we have seen. So here's a picture of an LED bulb. So these days we are seeing a lot of lighting being done with LEDs, and what you see here is that the way the physics of the LED works out, that it's a light emitting diode that puts out light but also dissipates a lot of heat. So that heat has to be taken away so that the temperature of the electronics is within a certain limit. So heat transfer becomes very crucial, and what has been done in this particular lamp you can see is that these are which take that heat and ultimately it is dissipated to the ambient atmosphere. So that's how this LED remains. So the way heat transfer takes place from these fins to the surrounding air is by convection. This is another example, and this is the motherboard of a desktop computer. So what we see here is a whole bunch of components on this, but one big thing that pops up here is this one. Below this is the main microprocessor, the chip, CPU, and on top, this shiny thing here, this is all aluminium, which is for conducting that heat away that the microprocessor generates, and on top of that is a fan. So what you have done here is that heat generated when the microprocessor does operations, that heat is quite substantial, and as we put more and more transistors on that chip and we drive it faster and faster, the heat generated, which is basically nothing but I square R heat dissipation, that increases, and so there is conduction taking place through this, and then we have taken the ambient air inside this box, blown over it, and that air takes away that heat. So this is an example of forced convection for cooling the chip. Just here behind it, you can see there's a thing with a lot of these pokey little things up here. This is another type of a heat sink. So there's no forced convection here, but this is by natural convection. Below that, there's the chip which is generating heat, and that heat has to be dissipated, and for that, this piece of aluminium has been put on it, and that takes away this heat. So this is a crucial thing, and it's there, you will see it in laptops and also in our cell phones and tablets and all the devices, that it is the rate at which we drive these things and the rate at which we can make things happen is limited by not by how many transistors we put on a chip, but how well we can cool them. So it's a heat transfer limitation that limits how much we can use these things for. Okay, this is an example from manufacturing, and what you are seeing and is a piece of steel here. You can get an idea how big this steel is. That this is a height of this is a man standing there, and it has been gripped by a crane, and it has been being brought out of a furnace. So this is a typical rotor material which has been heated, and then it goes out for forging, and ultimately we get rotors for say hydro turbines, steam turbines, and say gas turbines. The heating of this, and then while working it, it is hot, so you have very significant radiation also, but also a lot of convection heat transfer is taking place from it. There is no air being blown as such, but this piece, when it is moving, that is causing relative motion between the material and the air, and that will cause convection heat transfer to take place. So that's an example from one type of manufacturing. This is a picture of gas turbine blade. It's a simulation. So hot gases go over this blade like that from left to right, and the process they generate a force in the upward direction like that, and this acting on a lot of blades produces a torque on the drum, and that's how you get power output from this turbine. Now the gas temperature outside here 50 years back, it was 700 degrees Celsius. These days, it is close to 1600, 1700 degrees Celsius. The material used are very specialized type of materials, starting with nickel alloys. And these days, they also on top of that, they have a coating of a ceramic. But the thing is that you cannot allow the metal temperature to go that high. It will melt. So at 1600 degrees Celsius here, and a material here whose temperature you have to maintain below 1000 degrees Celsius is a big challenge in cooling it. So one of the designs of this blade is that inside the blade there are cavities which are running the entire height of the blade. Some air from the compressor, which has been compressed a bit, so its temperature is not ambient temperature but slightly higher, is bypassing the combustor and is brought into these blades, and it goes through these blades, through these passages, and cools this metal. Some of this is also injected out through holes in this blade, so it blankets the blade with a layer of relatively cold air. So this is a very, very crucial technology which has been seeing advances for the last 30-40 years. We are likely to see many more things happen in the next 10-20 years. The critical thing that has helped this thing to happen is convection heat transfer. This is an example of one of the air-conditioned trains on the railways. The reason I put it up here is that if we want to design the air conditioning system for these coaches, we need to know how much air conditioning capacity to put. So basically we are asking that there is certain amount of heat that is generated inside this coach and certain amount of energy getting into the coach because its temperature is less than the surrounding temperature. And then all of this energy has to be removed by the air conditioning system and thrown into the atmosphere. So one of the items in that, which determines the rate at which heat will go into the coach through the walls and the windows, is the outside heat transfer coefficient. So there is energy traveling from the ambient surrounding up to the surface, and then conduction through the walls of the coach, and then again from the coach walls it goes into the inside air, which is cooled. So this is the path that you have for energy heat transfer taking place into the coach. So how do we estimate first the outside heat transfer rate and then also the inside heat transfer rate? And this is a very long surface. You can see there are a lot of there's a break between coaches. There are various features on top of this. In the front of this locomotive, and this is a generator car which is producing electricity to power the air conditioning. And the question is, how do we decide what is the capacity of the air conditioning plant on each coach and what is the capacity of generation that is required on this train? So the outside part and the inside part heat transfer, these are determined by convection heat transfer. We now come to another application, and this is a automotive radiator. You can see the same thing also in air conditioning condensers, which are there in the outside units. So what you have done here is that you can see these long things are small thin walled tubes with the whole, and they are fixed between the top, which is a header here, and a bottom header. You have the hot coolant from the engine coming into the top. It is distributed into all these passages, goes through the tubes, comes into the lower passage and goes back as cooled fluid to cool the engine. And to keep it cool, between these plates we have put a lot of these thin aluminium sheets of this shape, which are called fins. So we have hot fluid going inside the tubes and giving energy to the tube material. From there it is conducted into the fins and also given to the air, and air is being sucked through or blown through these passages on the outside, which causes convection heat transfer on the fins and the outside surfaces of the tube. So how do we want to know what is the rate at which heat cooling takes place, and ideally you would like to make it more and more compact as possible. So we need to understand what is the rate at which the surface will exchange energy with the inside fluid, and what is the rate at which this outside surface will exchange energy with the air flowing over it. So there are two things going on together. So you have two convection conditions and one conduction through the tube and the fins. This is another example, and we are seeing a lot of these LED lights these days, and the same issue that LEDs are generating heat on this side, and on the back, as you can see, this funny looking thing is a heat sink to transport the heat away and keep the electronics in the plate inside this within a certain temperature. And this has to be out there in the open, so it gets all types of things that the climate can throw at it. It will get rain, it has to withstand storms, there will be dust on it, there will be birds sitting on it, everything is going to happen on this. And in spite of all of that, we expect that this thing will function properly and not just get too hot and blown up. So how do we design this part? That is a convection problem. So this is another of the type of lights. Coming back to computers, this is a slightly different thing. It is a GPU, graphics processing unit, and that is done for all type of image and movie type of things that you want to see. And also these cards are now used for computations, and we will come later in this course how it is used for heat transfer computations. So this is a card that does a very specialized set of operations, unlike a CPU, which is very general. It only does a whole bunch of matrix operations, and it has been optimized for it. We'll see why matrix operations are important in this. But what you see on this is that the load, that the card, which has chips on it, that is at the bottom, and on top of that, in this small thing, there are two fans. Because the GPU is generating so much heat that we need to then take that heat out to keep the chips within a certain temperature limit. So again, here you have how fast you can drive graphics, how fast depends on how fast you can cool it. So again, this is a picture of the radiator we were talking of. That was a sketch. This is an actual radiator, and we continuously want to make it better and better, more and more compact, and of course less and less expensive. Yet another application which is very, very widely used is called the shell and tube heat exchanger. A heat exchanger is a device where two fluids exchange energy. One is hot fluid, one is a cold fluid, without mixing. Many ways we can do it, but the most fundamental device is what is shown here. We separate the two fluids in this way. There is a shell, which is a cylindrical device here, and on top of that is this device here, which is called a tube plate. There is a similar tube plate at the other end. We have matching holes drilled in them, and we put a tube through this from one hole to the other, and at the ends we make it leak proof. And then this end gets fluid coming in from here, goes into these tubes, so it has a parallel path through so many tubes, goes through all of these, comes out on the outside and exits from there. The other fluid contained within this cylinder, the outside wall of the tubes and the ends of these tube plates. So this fluid comes in from outside over here through this opening, flows over these tubes, and in this particular design it then comes out here, turns around, goes up like this, then goes down there, then moves up this way, comes out there, and then finally exits from here. So that is the way this particular design is there, where one of the fluid is going in sort of a transverse direction to the tubes. That is one fluid, so it is flow over a tube, but not one tube, but a lot of tubes, which is called a tube bank. And inside this, the other fluid is flowing inside tubes. Energy transfer is taking place from one fluid to the wall of the tube. Then there is conduction through the walls of the tubes, and then finally that energy is transported to the fluid which is outside the tubes. So we have convection heat transfer on the outside, which is outside the tubes, flow over a tube. Convection heat transfer inside, which is flow inside the tube. So we have two different types of situations for which we require to know how can I estimate this heat transfer. This is a schematic of the same thing that I just explained, and here is a picture of what the actual device looks like. So this is fairly large in size. The tube diameter would be order of like 10-15 millimeters, and you can see the number of tubes that have been put in. In a typical, say, a power plant condenser of a 500 megawatt unit, there would be something like close to 50,000 tubes. And so here also you can see they are well beyond 100, maybe approaching 1,000 tubes in this one particular heat exchanger. But you can see clearly that this is the tube plate, and at the other end there is the other tube plate, and inside this all these tubes have been put in, held in place, and then we put the shell outside this. The finished device, there is an example of a finished device here. You can see that this is the shell. It has been mounted on supports, and instead of just having one heat exchanger, there is one over here, second over there, and there is a combination in which either of the two fluids can go either in parallel or in series between these. These are the finished ones, so the ends have been closed with an end cover with bolts on it, and this is the one which is still open and has not yet been closed there. So you can see the tube plate, the ends of the tube openings on this side, and on this side is the tube cover plate. Yet another example here is a motorcycle, and what you are seeing here is the engine, which has got the thing on it, which is here also there are some more fins, and the job of the fins is to take heat away from the cylinder to the air so that the temperature of the cylinder block is maintained within a particular temperature range. So this is a problem where you have either the motorcycle is stationary, in which case there is no wind on this, or it is in motion where there is a certain air coming on it, but instead of just coming on this, it has to go across the front suspension, then there is the front support, and then there is this exhaust pipe, and then it has to go out and distribute itself over it. So the airflow is quite complex in this particular case. And our objective is to make sure that this entire thing remains cool as far as possible as with a uniform temperature everywhere. So this is the last example, and here we are looking at liquid metal being poured into a mold, and what is happening inside this is that as the metal goes and fills the mold, there is a fluid flow over there. As it goes in, it begins to contact walls of the mold which are at a lower temperature. So there is heat transfer taking place to the walls, and in case the temperature drops down to the freezing point or the melting point of the material, you start seeing a phase change gradually, which is the latent heat being taken away, and the metal solidifies. So that's how we have to ensure that it doesn't solidify before the mold is completely full, and at the same time we have to make sure that the mold gets full completely with metal and there are no air pockets or bubbles in it. If those are there, then the component gets rejected from. So there's fluid flow here, there is convection heat transfer taking place. The material here is not air or water, but what you're seeing here is a liquid metal. That's another picture of a graphics card heat sink. There's a different shape and size that has been used in this particular case. Okay, so those are the examples that tell us that this life is so much more complicated. How do I go about predicting heat transfer rates in this? The basic question is, what is the heat transfer problem as far as convection is concerned? And very simply, it's a relation between heat transfer rate, which we denote by Q dot or small q dot, and a temperature difference that is enforced on the problem. And to make these two are connected by Newton's law of cooling, which says that the rate of heat transfer is proportional to the temperature difference between the surface and the fluid. We convert that into an equality sign by saying that Q dot is equal to H, which is a constant we call the heat transfer coefficient, multiplied by the temperature difference and a representative area over which this heat transfer is taking place, or in other way, the area on which this H is applied. So these two are connected in some sense, and the delta T is also of the area that you are looking at for heat transfer. So that's one thing that we require. In another form, we can write this as Q dot double prime, which says this is heat transfer watts per meter square. This is equal to H, the convection heat transfer coefficient, and delta T, the temperature difference. So the thing that comes out of this is that the units of H are watts per meter square per Kelvin. Now, very simply, the problem boils down to this. How do we get the value of H? Let's take the example of the motorcycle cylinder. A will be the area, total area of the outside surface, including the fins and the cylinder and everything else, nuts and bolts which are there on it. Delta T will be a temperature of the fin and the temperature of the air, the difference between them. While the temperature of the air can be taken to be nearly constant, the temperature of the fin may vary from point to point. There will be a certain amount of temperature differential at some point, some other temperature difference at some other point, and which delta T to take would be some sort of an average of all of that temperature. We would be lucky if the temperature of the fins everywhere is the same. In that case, this is very clearly defined that this is the surface temperature, or we'll call it the wall temperature, minus the ambient temperature, which we will denote by T infinity. If it is not uniform over the surface, then we break up the surface into small elements and apply this to that element where the temperature is uniform over that particular element. And then we add up the energy transferred from all the elements. So the working equation becomes then Q dot is equal to HA into delta T. The heat transfer rate is heat transfer coefficient, the area, and the temperature differential on which it acts. Getting H is what convection heat transfer is all about. And it sounds very simple, but it's fairly involved and actually quite complicated. What it depends on are too many factors, and that's one of the reasons why it becomes such a difficult thing. It first of all depends on the geometry of the surface which is in contact with the fluid. Then it depends on what fluid is there, and then what is the conditions of the fluid, what is its velocity, what is its temperature, and in general, when a fluid flow takes place over the surface, it generates something like what we call boundary layers, it generates turbulence, and that is what we call hydrodynamics of the flow. So you have so many complicating factors that are coming into play, and as we saw some of these few applications that I showed you, the geometry is different in each case. In many cases, the fluid was air. In some cases, like the gas turbine, it was hot gas on one side. Something moving through water has water in it. In the case of the molding, it was a liquid metal. So the thermophysical properties of the fluid, that is another variable. If we ignore that there is a temperature difference enforced on the problem, then we have only two things to worry about, the geometry and the velocity, which is linked by the hydrodynamics of the flow. So our first step is to say that, look, if I can understand the hydrodynamics, then from there I'll get some idea of what will happen if I enforce on that same problem a temperature difference. So we can say that we'll first study the flow over, say, the engine cylinder or the LED heat sink without wondering how much heat transfer is to take place. Look at what type of a flow takes place. Where is turbulent flow? Where do we have laminar flows? Is there a wake? Is there a separation? All those issues will come in. And then we'll say, okay, now on top of this, let's force a temperature difference and see what happens. So that's what we do. How do we get H? And historically, there have been two things what have been done. People said, well, I'll perform some experiments for that particular application. I'll heat it up at some point. Then I'll measure the temperatures. And I will do many such experiments for many such values of the experiment and then make a correlation out of that. That is one thing, and historically that's how we got things first, say about 70-80 years back. That's when the first of these things started coming out. The other approach is to do what we have learned in all our other courses, that if you are given a problem, write the equations that govern the problem and then solve those equations and you get the answer. The thing is, as we will see here, these equations are extremely complicated. They are nonlinear, inhomogeneous. On top of that, you have to apply these equations to complicated geometries, and that makes the solution of each and every problem, analytically at least, hopelessly complicated. And for very simple geometries, it has been done, but largely now this approach is no longer in use. But we do another thing, which is now the state of the art in heat transfer, which is we take these equations, discretize the domain and solve the equations for each point and get the answer at each point, and from there we get the value of H. That is the numerical approach. So what we are doing is that we have, say, the case of say LED, where you have the application which are that particular type of fins, and we could actually want to increase or decrease the shape and size of the fin to get the desired thing in engineering, which means that I would have to solve the equation many times over and over again. The fluid is unique there, and you have a boundary conditions combination. So what is the boundary condition? Is what is the heat being enforced on the surface? Are you enforcing a constant heat flux like an electric heater does or the chip does? Or are we enforcing a constant temperature condition, which is what would happen, say, when steam is condensing on the outside of a tube in a power plant condenser? So you have all these combinations coming in. Fluid has so many other variables. Boundary conditions have few more variables. And so solving a problem for every fluid at every time would make it very cumbersome. So what one does is to get solutions for certain cases and express the solution in a very general form, which is in a non-dimensional form. The non-dimensional form is nice in that you can then apply that particular thing to the same geometry but to any fluid within a certain velocity range, within a certain temperature range, and that makes the solution much more versatile. So that is what we end up doing finally. I'll give a few examples on what I mean by these two to illustrate how we get finally a correlation which is very versatile in use. Okay, let's take the example of the LED light, and we say, okay, the LED light is, I can simply make the fins in a two-dimensional form and say that, okay, this is my LED light, the back of the LED light, and of course in this plane it goes back here, a finite length at that point. Below this, maybe at some points or all over the place, we have our LED board sitting there which are generating heat. And the first option is, well, why do you have this sort of a thing? Why not just make it into a flat surface and leave it the way it is? So you have generated heat over there and leave it at that point. The light comes on this side, the heat is dissipated from here. So in some cases that would do the job. But what the engineers have found is that if I just do it like this and let it stand in air, it will generate a certain heat transfer rate, and the heat generation rate is such that the temperature of this surface will go to a certain value which is too high for the health of the electronics over here. So he said, look, that's not acceptable. I want to have more heat dissipation taking place and I want this temperature to come down. So in this case, we have a certain requirement of a Q dot or a Q dot double prime, which is generated by the LED, and the designer says that look, I am going to put 5 LEDs or 10 LEDs, which is going to generate so much heat, and I want the temperature at the electronics over there to be less than a certain value, say T max. So which means that we need to have a certain value of H that will do this, or H into A, that I can either increase A or increase H or increase both. And that way, this equation that we just wrote, Q dot is equal to HA delta T, this is done. And this T max is decided by the electronics. The other value, which comes in the delta T, is decided by the problem, that this has to operate in ambient air at a certain temperature. So we have to make a call, what is the maximum air temperature for which we are going to design this. If it has to be designed for a tropical climate, you might say, well, you better worry about going up to temperatures like 55 degrees Celsius, maybe even 60 degrees Celsius. If you are designing it for a coastal region where temperatures, say along the peninsula, they don't go beyond 35, 36 degrees Celsius, then that's a lower temperature. If you are designing the LED for operation in, say, Ladakh, then your temperatures are not that high, but then you have to also take on the fact that will it survive in minus 40 degrees Celsius. So that's how T infinity itself is a variable in this problem, but doesn't matter. We said that, okay, I am going to enforce a certain delta T, so I will design an experiment where I will not put this thing, but I will generate that heat by putting an electric heater below this. So we'll put an electric heater and measure the power that we give to this. So Q dot is known to us. We put a wattmeter there or a voltmeter and an ammeter, and if you have put DC supply, V into I will be the power there. And then I want to measure the temperatures of this. So we have an option of either fixing some thermocouples on this or taking an infrared picture of this, and from there we go back and get all the temperatures. So we put some devices, thermocouples for instance, on this, and we measure the temperature at some different locations, say T1, T2, T3, as many as we want. And that's another decision we have to take in designing the experiment. And then we put it in a chamber or in a surrounding where we are able to maintain this temperature up to in a fairly steady manner. Steady means what we have learned in thermodynamics, that d dt of everything has to be equal to 0. That means I have to create a chamber where this is generating heat, but the chamber is such that overall the air temperature does not vary within say plus minus half a degree Celsius. That's what we are seeing in the practical world. So we have T infinity, we decided what we are going to keep. So that will be, again we have an option, we have T infinity 1, that could be one value of temperature. Then you have T1, T2, T3, the thermocouples that you have put, and Q dot is again some variable we have. So we will vary these and say, look, I'll do my first set of experiments when there is no forced convection or there is no fan or anything blowing inside this chamber. I will just let it sit there and wait and wait and wait until none of these temperatures change with time. That means I have steady state in the heat transfer process. Once that is achieved, and that could take hours, we then say that, look, for this T infinity, the values of the surface temperatures were T1, T2 like that, and from this I get some sort of a representative mean wall temperature as TW. So we have a certain QW, we got this delta T done, and we say that, look, I have been able to compute these two. So I flip this equation and say that what I have here is that H is Q dot divided by A into delta T. So we measured Q dot with the power meter. A, we were able to measure from the geometry of what we put, whether it was a flat plate or this thing or with more of these things. And delta T is what we measured. And from here, we get value of H for that particular combination of T infinity, which was T infinity 1, and Q dot, say 1. And we have already fixed the area. That is one experiment. One data point has come. Then we say, well, I want to see what happens if this temperature goes up or this Q dot changes. So we do another experiment and say, well, look, now I will do this experiment for another T infinity, which is the T infinity 2, and maybe we give the same heat transfer rate, maybe Q dot 1 or some other heat transfer rate, say Q dot 1, the same heat transfer rate, and then see what is the temperature that we get. We measure it here, And so this, which was value h1, now we get value h2 over. So like that we keep doing experiments, and for different values of this we get different values of h. And what we do now have is a lot of data coming to us. So we have now a whole set of pairings there, that this is h, h1, h2 like that, and this, for this delta T was this much, delta T1, delta T2, and in all cases say we gave the same heat transfer rate. And this was for a particular geometry and for a particular air condition where we said the air is still, ambient is still. So from this we said that look, if I have to design something, then I know that for this geometry, if this is how the ambient is varying, then this is what the temperatures you will get. Now you decide what you want. Then we say, look, I'm going to change the design of the heat sink, and instead of those things, I will now put thinner ones and put more of these. Or say just put the same thing and make it thinner and longer. So now A has changed, but along with A, something else has also changed, is that the relative configuration of this with respect to the air, the hydrodynamics has changed. So we then say, okay, now let's test this one. And then you again do the same set of experiments, and again you generate a certain thing and say, well, for this particular geometry, this is geometry number 1, this is geometry number 2, this is the type of relation we get. And then we say, okay, these are type of geometries I looked at, now what about air? Suppose there is wind blowing on this, what will happen? Then we say, well, now I have many more combinations possible. I have this heat sink like this. I could have air blowing on it from the top like this, or air blowing across it like this, or air blowing like this, or any other combination of air flow directions. So again, you have that many more experiments coming up, and say, okay, we'll study a few of these. Let's take air flowing over this like this and see what happens. Or it could be that the heat sink may even be done upside down. So we take now that one particular combination, that velocity vector is the one parameter additionally that has come in. T infinity was already an issue with us. So we did all of these. Again, we repeated the experiment and got values of h like that. So we have now lots and lots of things coming up for different configurations of the same simple device. And the idea is, how do I use this to first get a correlation, and then how to use it in problem solving. The problem here is that which of these is the right design so that the electronics temperature is below, say, 60 degrees Celsius or 40 degrees Celsius, something like that. So that's what we do. And to generalize this problem, what we do is that instead of solving it each and every time, we say that, okay, in this particular case, this is the relation between h and some of the other parameters. Or in the forced convection case, between h and velocity. So we say that we are able to explicitly get what this expression is, and then we will non-dimensionalize it, which we will do later on, how we do that. And from there, we get that for this particular type of a geometry, this is what happens. Then we could generalize this further and say that, look, I have done a series of experiments for the length of the fin. So this is a correlation, that this is a correlation for L1, this is a correlation for L2, this is a correlation for L3, and then we can make a plot and say that, look, if your length of the fin is this much, then what is the h that you can expect? That becomes another chart which the designer can use. And so if we have to solve a problem, or you have to design a fin, this is what we will use. We will not go back and do all these experiments all over again. Okay, so this is an example of the experimental approach to what happens. The second approach that I mentioned was that we do what we learned in other courses, which is solve the equations. So what we do then is have a look, okay, here is the fins that I have. And this is sitting in still ambient air, and I have enforced a heating condition on this surface. So at this surface, I am pumping in some amount of heat into this metallic device. And then we say that, look, how do I compute, which equations do I solve that will tell me what is the temperature at all these places. That's the question that we are posing. And for that we said, look, we need to say, how does heat transfer take place from here to the fluid? So the first thing one does is say, look, what is the size of the airflow or the domain which matters in this problem? If this is, say, about size of an A4 sheet of paper, then this domain may be the size of a room. If I take it slightly bigger than the size of the paper, then your solution will be wrong. And that's the first thing that comes out, that when you are trying to solve it. So the equations that we write First is for the air now, conservation of mass, then the conservation of momentum, which is a vector, and finally conservation of energy. Three equations we need to solve simultaneously, we get the velocity field everywhere. So if we are good enough in solving it, and we say that look, everywhere here the temperature is the same, and how much heat transfer will that be? In that case, we will be solving and getting an answer, and the answer will be that at each point in this domain here, either analytically we will get it at every point in this domain, or numerically at discrete points in this domain, we will know what is the velocity components u, v and w, and we will also know what is the temperature at that point. That will tell us what else is going to be happening over here, and from there we then go and say, well, what is the rate at which heat transfer took place from the surface? The surface temperature was something, and that gives us the gradient of temperature normal to the wall. So I can get the temperature gradient here, the temperature gradient here, the temperature gradients over there. That means in this direction, the temperature here was this much, here is this much, here is this much, and here is this much. From this data, we go back and then compute the wall temperature gradient and get what the value of H at that point for a small area, and this we call Hx, which is a local heat transfer coefficient applicable to a small area. Its temperature we have known, so we know what is the heat transfer rate from here, and then we integrate it over the entire surface and then get what is the total Q dot that we were getting over there. That divided by some representative delta T into A, this will be the value of H. So without doing experiments, we got this correlation. Now we can do the same thing, that air is not still, but we have put a second condition that air is blowing in this direction, and we get a similar solution for this. Like that, we then again keep doing again and again solutions and generalize them and say, look, if this is the air velocity, this is what I get. So that's what we have, that's what the solving of equations would mean. It looks very simple as I am making it out, but when we look at these equations, they will be very, very complicated. Maybe you have already seen the mass and momentum conservation equations in a fluid mechanics course. We will now be adding here also the energy equation. And this is what causes the problem to become so complex. The other thing is that the solutions that we have developed are unique for this particular geometry. If we had some other geometry, for example, I said that, look, I will make I'll make a fin like this and then again make a fin like that on that, I cannot apply this. So it could be possible that we make these type of complex fins, and in the CPU problem you did see these type of fins. Or somebody says, I won't make these straight in a rectangular thing, I will make them circular. Is that better? Somebody says, no, you don't make it completely straight like this, make it a small here, then give a break, then make it like this. All things are possible to achieve the desired condition with the minimum amount of material and minimum amount of still dissipating that heat. So some of these correlations we can qualitatively extrapolate, but exact solution would still require either an experimental approach or a numerical approach. What we do to get these type of solutions for what we are looking at heat transfer. And the same thing we would do for the other application, for example, the motorcycle engine. That's how the engineers actually make those fins and say, look, can I now increase the fin, decrease the fin, things like that. One of the things we would like to look at, we say that fine, in the case of the LED, I was only interested in dissipating this total amount of heat. But in other applications, like say the gas turbine blade, where you have say a passage like this, and so there's a cooling passage over there through which cold fluid is going normal to the paper and hot fluid is going over this. What happens in this case is that if there is a constant heat transfer happening through this from here to the here, that means there is convection taking place into this surface, conduction taking place everywhere inside this metal, and then finally convection to the fluid going inside. So here you have to look at this problem somewhat separately, because this is flow inside a passage, and an additional complexity that comes in that this passage is rotating. It is not a stationary passage, and that generates Coriolis forces and all these type of things. The flow outside the blade can be treated as a more classical flow over an aerofoil, And that tells us the flow over this is governed by the type of boundary layer that it will build up. Say a boundary layer over there and say a boundary layer over there. And this is a hydrodynamic boundary layer. And we know from fluid mechanics that the local heat skin friction coefficient at these places will be different. What it tells us is that the local heat transfer coefficients here will be very drastically different, which means that the surface will not be at a uniform temperature. So there will be some temperature here, some other temperature here, somewhere it will be very cool, somewhere it will be very hot. And now the designer wants that I not only want to cool it, but my objective is that the temperature everywhere at each point, local temperature, should be less than a certain value. So if we have half the blade within this limit, we have only solved half the problem, but the blade is not acceptable. We need to now do all sorts of things to make sure that regions which are running hot, we are able to bring the temperature down there also. So this is an issue where we have to worry about what happens to the local temperatures. Another example, say from manufacturing, would be that we have a part which has been, say, forged, or we want to heat treat this thing, say a piston pin. So you have heated this, and then we suddenly dip it into a cold oil or cold ambient water. And if this has been heated to 600 degrees Celsius and then plunged, we know that suddenly you have vigorous boiling and all sorts of taking place. And what it does is there's a heat transfer happening through this, and then inside this also by conduction, heat transfer is taking place over there. But this is not an instantaneous process where temperature everywhere inside is uniform. What happens is that in this, when there's cooling taking place on the outside, say by boiling or just by convection through air, then there are certain parts of this closer to the surface which are going to cool faster than the points which are in the inside. That is one issue. So there's a radial dependence of temperature. And the second is the point here on the surface, the point here on the surface, and the point here on the surface, they will cool at different rates. This point, if will cool say the fastest, this will be a little slower, this will be the slowest. So what it does is that this point, its temperature will keep going down, this won't go up, so this will, because of thermal expansion, this will start to contract, this will remain expanded, it will generate stresses inside this material, and even due to temperatures gradient like this, it will generate stresses, and chances are there could be cracks in the material. Another thing that can happen is, because of these temperature differences, if you have a long cylindrical shaft like this, say a steam turbine rotor, it is hot and it has been stopped, and we just allow it to cool in still air. This tells us that this part will cool at some rate, this part will cool at some rate, and finally, after it has come down to ambient temperature, this will take a shape which is like this. Because of thermal stresses, this shaft will bend, and this becomes so severe that when it is sitting in its bearings, these are the hydrodynamic bearings at the end, this shaft can no longer move. It gets jammed in the bearings, and now you have a very big problem. You cannot not only turn it, but you now have completely open the turbine, lift the whole rotor out, send it back to the manufacturer, who will slowly anneal it, bring it back to the same straightness, and then send it back. Lot of money, loss of generation because now the turbine is out, and on top of that, the cost of repairing. So this is where heat transfer convection comes in and says, well, look, if a rotor has to cool, don't let it stand still. Slowly keep rotating so that all the upper surfaces keep rotating, cooling at about the same rate, and so you won't have the bending of the rotor. That's the type of insight convection heat transfer gives to us. So those are examples and the type of things that happens. We now start classifying what type of problems we get in convection heat transfer, and that is somewhat linked intimately to what happens in the fluid dynamics of the flow. So we are going back to fluid mechanics that you have learned and revisit and say, look, what is the general way in which I can begin to understand fluid flow problems. That is central to heat transfer, convection heat transfer. So broadly speaking, fluid dynamics flows can be classified as external flows or internal flows. What we mean is that in an external flow, we have an object, say an aerofoil or a cylinder or anything, and this is in a domain which has a flow relative to it, where the fluid has no other surface in any other direction. So there are no other surfaces in this problem. The fluid may be stationary. If the fluid is stationary and this is stationary, there is nothing to be done in fluid mechanics. But if it is heat transfer and this surface is hot or cold, we have a heat transfer problem. But that in turn induces a convection fluid flow problem. So we have flow there, and we could say that, well, this flow can be in some direction, and for simplicity we say the flow is unidirectional, left to right, and also in the third dimension there is no variation. So there is no other surface, and the simplest thing is there is flow taking place over this. And in fluid mechanics we ask the question, what is the pressure on this surface, what is the force that it acting on it, what is the drag force that is experiences. That is what was interest to us in fluid mechanics. In heat transfer we say that, look, if I have heated this surface, what will be the heat transfer rate in this exactly the same situation, and also what will be the drag on it. And you ask the question, are the two related in some way? This is what you have in an external flow, and what we do in this case, the simplest possible thing that we had looked at was not an aerofoil or a cylinder or some other shape like the motorcycle cylinder, a thin, smooth, flat plate. A flat plate or a flat surface, whatever you want to call it. And we are saying that this plate is aligned with the mean direction of the flow. We could have the condition that the plate is like this, but the flow comes on it like that. That's not what we are looking at. We said the simplest of the simple configurations in external flow is flow over a flat plate. And if you ask, well, where is the practical application of this? It's practically difficult to cite anything. Everything is a little more complex and complicated. You said, I want to make it in the lab. How do I do it? Well, okay, I can make this flow, making a very large room and establishing a uniform flow, which is what you do in a wind tunnel. And so I will have a thin plate. Well, thin maybe is a qualitative word in the practical sense. Is it 0.1 millimeter or 1 millimeter or 2 millimeters thick? And the edge has to be very smooth. That is another thing. We'll say smooth. Well, we know that in manufacturing, there's a surface roughness always associated with these, all surfaces. So how do we define what is smooth? And flat. What is flatness? In practical, this plate will always be slightly wavy. So what is it that qualifies as these very three simple assumptions that we have made? And then we say, I will align it with the flow. So if assuming that we made a very nice uniform flow, how do I make sure that the plate is exactly aligned like this? Well, in the real world, it will be off within, say, maybe plus minus half a degree, 0.1 degree, 0.2 degree. It will not be 0 degree. But in theory, we take it as 0. But leaving the real life problems aside, we say that we study this for the simple reason that it tells us what will happen, and from here we can extrapolate that to what happens on this type of a surface, what happens to a cylinder, what happens to the motorcycle cylinder, what happens to the fins of the LED, and so many other things. So those were all examples of external flow. So this is the simplest possible configuration that we will study even in convection heat transfer to begin with. In internal flows, the simplest configuration is a circular tube. So we note that by its center line, into which the fluid has entered through a very smooth entry. So this could either be pumped from this side or be sucked at the other end, but we have made a very nice smooth entry which gives us the condition that when the tube begins, which is some physical point somewhere on the tube, that the velocity at every point is the same, the local velocity. This is an assumption, an idealization. And we are going for this idealization because this lets us understand what happens inside this tube. The hydrodynamics tells us that in this case, the fluid right adjacent to this plate, this is in a way stuck to the surface. So it has the same velocity at the surface. And this is what we call the no slip boundary condition. The next fluid element moving here is going to slide over it. So there is relative motion between two elements, which means there is friction there. So there will be shear force. So the next element will be there, which will be sliding on top of that. And as you go further up, the next element will be sliding on it until finally you will reach a point where this element does not feel the effect of the plate. So that's very quickly what happens and what we call the growth of a boundary layer. The same thing happens in this locally. You said it doesn't matter what the big tube does, but for a very small distance inside this tube, as soon as the fluid begins to move it, this surface, even though it is circular, locally I can think of it as a very small straight surface with adjoining straight surfaces, and very thin boundary layers will start to build up over there. And this will happen all along the circumference, so it will be like a annular boundary layer that is building up. And these boundary layers will continue to grow, because of which what will happen is, at this point, this fluid will have accelerated a bit, this fluid has stopped, and some gradient is there in the fluid over there. And in fluid mechanics we have learned that if you allow this to go on for a long time, after some point you will get a particular profile there, which for a laminar flow, that means the velocity at all these points, it has a parabolic shape. For laminar flow, or it has a slightly different shape, which is sort of a more flatter shape for a turbulent flow. So that's what the hydrodynamics tells us, and this is the simplest of the case with the simplest of these assumptions. In reality, tubes may not be exactly straight, there will be some roughnesses in it, and like in the case of these days automotive radiators, you could also put some other materials inside this to make the surface rough. Then you have the inlet being very smooth. I showed you some pictures of the shell and tube heat exchangers where we have put a lot of tubes together. And these were fixed into the tube plate. And all this box was closed, and at one end of this was the inlet pipe. So question becomes, what is the flow like from here into all these tubes? Do I have the same flow in every tube? Is this sort of an inlet boundary condition justified? Well, the simplest thing is that what happens is, because this is coming like this, the flow here will bend and come like this flow will bend and go there, this flow will bend and go there. This idealization may not exist. But this is again a bit too complex to look at, and so before we go to that and actually use it in designs, we'll say, okay, first I will understand what happens in this problem, then I will go to the real problem. Okay, so these are the two most fundamental things here. This is flow inside a smooth entry into a tube. That is one type of flow we get, and flow over a flat plate. This is the second, external flow. These are the two simplest conditions that we can look at from what we have learned in fluid mechanics. What is common to both is that the fluid has been set in motion in both these cases by something else, an external agent. What we have is that here we always looked at the case where the fluid was in motion. What that means is that either you have air being blown over this with a fan or a wind, say a blower. That is one possibility. So there's a fan, or in the case of a tube, you have a pump which has pumped this liquid into this and forcing it through this. So these are things are there, and your device is stationary. The other thing is that the surface itself could be in motion in still air. And that's what happens in an aeroplane, that the wing of an aircraft is actually moving through air, which to begin with we are assuming it to be still air, and for analysis we do exactly the opposite of it. We keep the airfoil fixed and let the air move on it in the opposite direction with equal magnitude. The problem is the same. Same thing we have to do with an automobile or a motorcycle or a train, but there is a complexity. In that you have a surface road on which this vehicle is moving, and if I have to create exactly the opposite situation like we did for the aeroplane, I will not only have to make the vehicle stationary and put airflow on it in equal magnitude on the opposite direction, but this road also has to be made moving. Only then the fluid mechanics will be preserved. This is quite a bit more complicated. Or we could have any other combination that both are in motion, that blade has, the surface has a certain velocity and the fluid has some other velocity. This is also possible. And the best example of that is the aeroplane itself, that the plane is moving in a particular direction and it is experiencing wind in some other direction coming on to it. So it may not be that both are aligned with each other, but it could also be that this is like this and flow is at some tangent to this. Entirely possible. So this is the first thing that is happening, that all these type of problems where the fluid has been set in motion, this is called, the heat transfer part of it will be called forced convection heat transfer. So you have a fluid flow, you have a fluid mechanics problem on hand, and we are adding this additionality to it by saying that in this case, if this tube wall were at a higher temperature than this fluid temperature, what happens? In this case, if the surface is hotter than the air or colder than the air, what happens? So we have said, well, the fluid mechanics happens anyway. Additional to that, something else also happens, which is convection happens. So how do we analyze that? That we'll come to that in a little while. But this is the first thing that we have come across. What is forced convection? What it tells us that when we mean by, say, forced convection, is that the temperature fields that the fluid experiences, it does not generate anything which affects the fluid mechanics. So if in this case, say the airfoil were hot and the air outside was cold, then as the air went out, the air got hot. And what we are saying is that that temperature change of the air does not affect the flow that was happening on it. The boundary layer and the fluid, that is not affected. So the heat transfer effect is delinked from the fluid flow. That means the conservation of mass and momentum equations that one solved in fluid mechanics would still be applicable here. They do not have any dependence on temperature, except in one way, that because the fluid that came here or the fluid that was going here, its temperature changed. That temperature change caused a change in the properties of the fluid itself. This is an important complicating factor in forced convection. That heat transfer causes the fluid properties to change, whereas fluid mechanics, as you learned, it was isothermal flow, so there was no question of fluid properties changing. You had a certain temperature and you evaluated all properties at that temperature and you got what you wanted. This is the additionality that has come in here. Temperature dependent property mu T. There is yet another possibility in convection which fluid mechanics has not even looked at in a classical fluid mechanics course. What happens in what we call natural convection? And here we'll again look back and say, look at the case of external flow. And the simplest, there could be said, like I showed the forging rotor in that case, that was a cylinder normal to the paper in say still air. Or we could take a very simple case that, say, for example, the LED light which did not have the fins but was standing vertically. This could be considered to be a vertical plate which is being heated. And this surface is sitting in air which is still. That means this air has no velocity. What happens on Earth is something like this. We have gravity acting in this direction. What it means is that this fluid which was here next to this surface, say the surface was heated, this element had a temperature more than the temperature over here. And because there is a body force field being applied, this will experience a force and this will cause the fluid to go into motion. So this fluid element here will start moving up. It will induce an element further away from it to move because of viscous effects. This fluid will begin to move and pretty soon you have established a flow around this. What this means is that this flow took place because the temperature gradient was forced on the fluid and there was a body force field in there. This thing where temperature difference induces a flow is called natural convection. What I've shown here is a particular class of natural convection where there is a heated object sitting in a still air where there are no other surfaces on any side. This is termed as, and there are just as many problems that we see in the real world where free convection actually takes place and we have to really worry about it. In general, the heat transfer rates from free convection are very, very small compared to forced convection. In some cases, we can cause some more external flow to take place, but there are many cases where you cannot, and you have to learn to live with this. So this is an important thing. So external flow does this, and now take an example of internal flow. We'll look at a couple of examples. The first one we'll look at is a vertical tube or an inclined tube. Where do we see such a thing? In solar water heaters. The tube is not vertical but inclined at an angle so that sunlight is as far as possible normal to the surface. And inside this tube we have water. And this is connected in a circuit. It comes from somewhere and goes somewhere. And what we rely on is that as this tube surface gets hot, the fluid gets hot, and because of temperature gradients within the fluid, this fluid is set in motion. So there is no external thing here, but temperature gradients within the domain is what's causing this flow to take place. This is an example of natural circulation. Internal flow. You also encounter the same thing in many types of boilers and power plants where you have a long tube which is heated on the outside by gases or by a flame, and we just allow water to rise through it as it gets hot, and in some cases also we maybe allow it to boil as it goes out of this. But this is an example where the flow is established by temperature gradients, just like what we saw in external flows free convection. Another example would be where you have, say, two rotating cylinders, one cylinder fixed and say one cylinder rotating. So this internal one is rotating, this one is fixed. And that's what you see basically in, say, a journal bearing. This is what you see in every electric motor and electric generator where the rotor is rotating and this one is stationary. And in between you have air. The fluid mechanics part of the problem can be solved, and you say that this fluid will have the same velocity as this fluid is stationary, and in the end you will establish a certain velocity profile which you have probably heard of as solid body rotation. Now what has happened is, if there was no temperature difference, then that fluid mechanics solution was good enough. What is happening now is that we, in the heat transfer part of the problem, we say that, this is the rotor, there is current flowing through the coils, it is getting heated up. So we say that this temperature is now hot, this temperature is relatively cold, so I have enforced a temperature gradient across this gap, air gap. Now because of this, there is omega square R that introduces a body force field. On top of that body force field, we have introduced a temperature gradient, and now we start getting a different type of a problem, which is called here, as I called here, natural convection. It took a long time for people to realize why electric motors were burning up so fast, for they thought that in this gap in the motor, we will put a fan and we will blow air through this fan, through this gap. And they calculated that, okay, this is an internal flow, something like an annular tube, and with forced convection equations, we will calculate heat transfer coefficient, and that we can predict what the temperature should be. When they did the design on that basis, it did not solve the problem. Rotors continued to burn out unless they looked at this part of the issue. They realized, well, there is not forced convection taking place, but natural convection taking place, and because of that, heat transfer rates are much lower than what force convection was predicting. And so now you have to redesign the device from very different perspective so that temperatures remain within limits. So the important thing that we have seen here compared to what was there in the earlier case was that in natural convection, it is the temperature gradient that generates fluid flow. And of course, the fluid flow obeys the same laws of conservation of mass and momentum that we had learnt in fluid mechanics. It's the same thing. What it means is that because the temperature gradient is causing a fluid flow, and as we saw here that buoyancy is coming in, what it tells us is that we have produced a force on that fluid element, which means that the momentum equation will have this force coming into it, and that force came because of temperature gradient, which means that the momentum equation explicitly has temperature in it. So the nature of the equation has undergone a major change when we look at natural convection, something that was not happening in forced convection. The temperature did not directly come into the momentum equation at all. The effect of temperature on properties is very much there here also. So that's something we have to consider. So this is what we have now seen, that we have four very fundamental configurations that we study. We develop the theory for it. We learn insights from that. We learn the basics from it and say that, look, this is pretty robust fundamentals which we will apply to any complex heat transfer problem. That is the approach that we take. So what we have here is four basic configurations that have come out. And these are that in forced convection, we take flow past a plate aligned with the flow. So this is a uniform, steady flow, velocity u infinity. And in the companion heat transfer problem, we now also have to say what is its temperature. This is T infinity. And we have a plate whose geometry is, say, length is L, and it is either heated or cooled. And we have two ideal conditions in that. Either we say that its temperature is constant everywhere, Tw, or the heat transfer rate per unit area is constant, which is Q dot double prime. In practice, Q dot double prime is what we get when we apply an electric heater. If you have an electric wire with constant resistance and a current fit, I square R heat generation in the wire is constant. So same thing will happen with a foil or a plate. That's how we can generate a constant heat flux wall. And that we call iso heat flux. The second thing is we can get constant wall temperature, and this comes in many devices where there is a phase change taking place. Say in a evaporator or a condenser, we have fluid on one side which is undergoing a phase change, so the surface is maintained at constant temperature because during phase change temperature change does not occur, and the other fluid experiences a wall at constant temperature, not the fluid that changes. In many cases, the real surfaces may not have either of these two. For example, if you have hot water going from one side coming out as cold water and hot air going on one side and coming out as cold air, the surface will neither be constant temperature wall, neither will the tube will be a constant heat flux wall. That is an additional complexity which we will not worry about right now. We said, look, let's make it as well behaved as possible so I can at least begin to understand what happens in this. So that's TW and Q dot double prime specified for this. So that's one fundamental external flow configuration in forced convection. In free convection, we just said that we have a vertical flat plate sitting in a field, a force field, which is in our case. You can think that when you go to the International Space Station, where this part is not there, what will happen to heat transfer? Which equations we will learn, but then qualitatively if we can argue, well, what does gravity do to cooling of an electronic component in the space station? That's something you can think about. G is a player in at least one case, but I'm saying that G is not the only player. It could be any other body force field. The electric field, magnetic field, if the fluid is influenced by that, it could happen. In natural convection, sorry, this was natural convection. and both these are external flows. We now look at internal flows, and in internal flow we will study in detail the simplest thing, which is smooth flow coming into a tube. This is our force convection problem. It comes with velocity u infinity, comes with temperature T infinity. In this case also we enforce a wall condition, either this or this. It has got a length L and fluid everywhere is maintained at T infinity. Here we do this thing and say, okay, I have now more parameters into the problem. Geometrically, I have the diameter of this tube to worry about and the length of the tube to worry about. Here it is length and normal to the paper is W, which we assume that there is no effect in the transverse direction. It's an assumption. In the real world, this too is not too well behaved. So is internal flow force convection and internal flow natural convection, where either we could look at the tube or we look at the fact that you have this surface and we'll put a second surface, but join up these two to make a closed thing and say that this surface is at a higher temperature, this is at a lower temperature, there is some fluid in this. This could be either a tube. Now, tube of course it does not have two surfaces, but this could be like a wall, an infinitely long big wall with a small gap in it. What does this do? Or that gap could be big, that depends on it. Or we could look at what I just drawn was a tube and see how to deal with these things. So these are the type of problems that we will begin to look at, and the way we will develop our understanding, we will start from here. What we learn here is partly applicable here, partly applicable here, applicable here. So this basic form is very good to get the basics right for many applications. So that's what we will start with. Flow over a flat plate and let to a forced flow over a flat plate. We'll look at the hydrodynamic boundary layer growth. We'll look at the thermal boundary layer growth. Then we'll derive the equations for this and say, look, what is it? So we'll come to a point where we say, now I know what equation I have to solve, but the fact is none of us will be able to solve it. So at that point we take two things. One, we get the ability to solve these equations on a computer, which is CFD or CHT. And second, we learn how we use correlations to get the solutions that we are looking. That will be our strategy for understanding this thing. So the fundamental thing here, and now we'll start going into this, is what happens at this surface. And on this, we have this fluid coming up. Uniform velocity everywhere. And we say that if I have this temperature at a certain, this plate at a certain temperature, which is different from this, so this is U infinity, T infinity, and let's say for the simple case, this is at a wall temperature TW. In fluid mechanics, the whole action would have been that if this temperature gradient difference was not there, we would ask the question, why do I study this plate in fluid mechanics? I want to know, say, the drag force on the plate. And many applications, this is the thing that we want. A plane is flying through air, well, how much force is it experiencing? Or the opposite part, that if I put a fan or a blower or a ceiling fan, the blade is imparting momentum to the fluid. For that, I need to worry about the drag coming on that. Or even more fundamental, wall shear stress. That is what we are worried about in those cases. And we say, well, how can I calculate the force experienced by this plate? Which equation do I need to solve? Like in heat transfer, you can do an experiment. Take this plate, put it in a wind tunnel, put it on a load cell, measure the force. Fine, one gets the answer. What happens here is that I want to solve the equations, and we say, fine, we have learned that we have conservation of mass and conservation of, say, x momentum, and maybe conservation of y momentum. So we are establishing our reference frame. This is x, this is y, and we'll say that this edge of the plate where the fluid first contacts this is the leading edge. This is the trailing edge. This flow which has come up to this point, this is the upstream flow. And the flow after it leaves the plate, we can say that this is the downstream flow, and it will produce in its at the back what is called a wake. And so now I want to get the force on this plate. So we say that the drag force, this I will get the drag force for every elemental area, say at this point on this little element, multiplied by dA, which is unit length normal to the paper multiplied by delta x, and integrate it from 0 to n, the length of the plate. Thing is, fx is a function of x. That means the local drag force is a function of x, and we relate it to the skin friction coefficient Cfx. We know what is this. That means the skin friction coefficient in this element is different from that in this element, is different from this element, is different from this element, which is why we have to make this integration. And then you say, no, I need to calculate Cfx. That means at every point, what is the skin friction coefficient? That means locally, what is the force on this, the drag force normalized on the characteristic drag force, which is, say, the local force, which will be, say, Fx, and it is normalized on a force, characteristic force in it, which is half rho. This makes it non-dimensional also. So this is what we need to do, is to calculate the skin friction coefficient at every little element on this and integrate on it. And so how can I get that from solving the equations? Well, the thing to do is to set up these equations and then solve them explicitly, which will give you a solution of the form u as a function of x, y everywhere in the domain, v component of velocity as a function of x, y everywhere in the domain, and pressure the function of x, y everywhere in the domain. This will be our answer. That's what we will solve for. These equations, that's what they tell us. So we have the solution here, 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 like that, here at every point, here at every point, and from there we need to calculate the skin friction coefficient of the drag force. And for that, what we do is, say, we get this data and we realize that wall shear stress is mu du dy calculated at the wall or at the surface. This is tau xy or tau wall. So what we are doing is that at this point we say this is the velocity, this point this is the velocity, this point this is the velocity, this point this is the velocity, and if you go far away, the velocity will become u infinity. So we fit a curve to this and get the gradient at this point, and that is du dy. And that gives us the local wall shear stress. From there you can get the local skin friction coefficient, and then we can put it in this equation, integrate it, and get the drag force. So fairly complicated way to get the answer. What one does these days is say, yes, I will solve this equation. For a laminar boundary layer, for some simple cases, there is an explicit solution. The exact solution is there. In the practical world, what we do these days is to say that, look, I will solve this equation numerically, which means that I will define my domain, which is a big thing like this. I will just make small elements all over the place, everywhere, including here, including there, and get millions of these elements. I can change the shape and size and location depending on various considerations, and then we will write the equation at each one of these and solve them. So we come to numerical methods like finite element method, finite difference technique, finite volume technique, and if you solve all of that, we will get this answer, not as a continuous function of x and y, but u, v, p at each one of these points. That is what the answer of the solution will be, the simulation will be. After that, what we do is exactly the same, that we draw this profile, get the gradient, and see what happens. So this is bringing in a very important fact, that if we have a plate, the fluid next to it has the same velocity as the wall velocity, which we are assuming it to be 0, and we say that u, w or vw, this is 0, this is u infinity, and what we learned was that at the leading edge, every element will have the same velocity u infinity. A little away, this element, fluid element, is stuck to the wall, and the other elements are going past it, but because it experiences a drag, it cannot go as fast as u infinity. So here you had u infinity, but here you have less velocity, and here you have even less velocity. And I'm only drawing the u component. Further away, everywhere it is the same velocity, which is u infinity. Further down, the drag has now had its effect. It has slowed down elements further away from it. So you have an element here which has u infinity, and elements below this, they all have less velocity. So you got velocity profile like that. And then outside this, it is flat. That means there is a certain region, and we take these points where u infinity is there, we will get a locus of points where outside this the velocity is u infinity. That means the fluid element here has not experienced the presence of a plate. Whereas all the elements inside this, they have their velocity slowed down, and as we will see later, some of them also got a v component coming in there, because of which this entire region has experienced the presence of a plate or the surface. Velocities everywhere are less than u infinity, and this whole region, this entire region there, this is what we call the boundary layer, or to be more specific, hydrodynamic boundary layer. Everything here is same as what we had learned from fluid mechanics. So there is the edge of the boundary layer, which you can show that by a line, and the boundary layer growth ends where the plate ends. So the plate has say ended here. After this, there is no boundary layer at the back. We don't call it a boundary layer. But what happens is, in this plane, the velocity here was 0, velocity here was u infinity. So you have a velocity profile like this, and further down, there is no plate anymore. So this element which was stationary, gradually it begins to get a small velocity. This element is dragging the next element down. So this dimension grows, but this velocity at the center slightly increases. And that is a totally different region, which is the wake. Okay, so that's what has happened. And the central idea of both fluid mechanics and convection heat transfer is that this is where everything happens. What happens at local skin friction coefficient at this point is determined by the solution of this whole domain. We cannot just solve the equation for a small region and say this is the skin friction coefficient at this point. Not done. Every fluid element has experienced some way or the other what is happening here. And the final solution, whether analytical or a computer solution, we have to take a domain which includes the boundary layer and a lot of fluid on all sides of it. Only then our answer is going to be correct. Once we know that boundary layer data has come, then we can move on and calculate the drag force. We will add to this now that instead of being an isothermal problem, I now have this surface at a temperature which is say greater than or less than the incoming fluid temperature T infinity. But before we do that, I'll show you some pictures about the evidence of the boundary layer and why ultimately fluid flow problems and convection heat transfer problems boil down to understanding what happens inside the boundary layer and in some way manipulating what the boundary layer does. So we'll look at some pictures, and here's a picture. What they have done in this experiment is that on the bottom you see a surface, and above it is water which is flowing over it. The water is flowing at has come onto a uniform velocity. This surface is much longer behind it also, so that's where it started. But at this point, what they have done is they have kept this very thin wire. And what's done into this wire is that momentarily they passed a high current through this, and that caused electrolysis to take place here, and it released lots of very small bubbles in this. Bubbles are so small that we can ignore the effect of buoyancy because viscosity is dominating. And then after a while, this photograph has been taken. So at some instant of time, what you see is that the bubbles which started off along this wire at some instant of time, after some time, they have taken up this shape. That means the bubble that started here has reached here, the bubble that started here has reached there, the bubble that started here has reached here, the bubble that started here reached here, and the bubble here has not gone anywhere. So this is the profile that I was just explaining to you. And if you had taken snapshots of this, then initially it would have been a straight line, then it would have been a line like this, then a line that would have come like that, and now this, and after some time maybe it will go off there and make a line like that. You can see here that all the bubbles have gone in a very nice straight line. There is no randomness in this, they are not mixing with each other, and that is the classical property of a laminar flow. And this is what you are seeing is the typical gaseous boundary layer profile on a flat plate for a laminar flow. Okay, here's the second picture. This is a flat plate at zero angle of incidence, and it is in a flow of water. And photograph has been taken by putting very small particles, they said here, air bubbles in water. So introduce very small air bubbles like with the wire that we had, and you see how the bubbles are flowing. And what one sees is here is that this is the plate and a very, very thin region which is black in color, and at the back you see this particular region. This is the boundary layer that is grown on this plate. And the important thing is that the thickness of the boundary layer is very small compared to the length of the plate. That's an important assumption that we'll see when we write the equations for the boundary layer. So that's another picture there. Now here you see two pictures, and what you're seeing here is airflow coming from left to right, and what is here is a plate with rectangular holes in it. And at the back, what they have done is they have taken a wire. On that wire, they have put a very thin layer of oil, and after establishing the flow, momentarily they passed a current through the wire. The oil evaporates, and immediately after leaving the wire, it condenses to form very small droplets of water. Okay, yes. Sorry, there has been a power disruption here. So what I'll do is we have run out of time now. So I'll continue from what I was discussing here, and tomorrow's lecture we'll pick it up from here. Then we'll look at boundary layers and the condition equations. Okay, so thank you.